Okay, so in the last episode, episode 10, basically spent an hour trying to make my code more readable, more object-oriented, and, actually I didn't optimize. It's probably something I should have done, but that would have made the episode like 2 hours long. So, let me just quickly go over what we did. So we created the world class, which allows us, for now, to just set some test objects and then a size of our view plane as well as a background color. We created the view plane class, which allowed us to specify a width and a height as well as a pixel size. And then we created these 3 classes: our sample class, which was our base class, holds the number of samples, as well as an abstract method for determining the x and y point, the x and y values that will be utilized for making the ray in our tracer class. Then we have regular and jittered sample. Both implement that abstract method. It extends sample, so these are derived classes. Regular sampling is taking the center of each sample, and then jittered sampling is a random value. What else did we do? We created a projection base class, which I'll be going over more in this episode, but for now we just have an abstract class, create ray, which returns a ray based on point value determined by the sampling done. And then I implemented the orthographic create ray method, which simply defines the point for the ray as well as the vector, in this case in the negative z direction for the vector, and then the view plane is 100 units along the positive z axis. We'll modify this later to be customizable and whatnot. Then we created the tracer class. In this tracer class we take the x and y pixels, we create a default black color and a variable indicating whether or not an object was hit. Then we loop through the rows and columns for anti-aliasing. We create a 2D point, which will be utilized for the x and y values for creating our array in terms of the origin field. So this inputs the row, column, and x and y values. Then we create the array. In this case we were using, as you can see, this is abstracted, so you don't really need to know whether it's orthographic or perspective, fisheye, etc. So that returns array. Then we create a min value. This is obviously set to the max to the beginning, and then a temporary color, which is set to the background. Then we loop through each object in our world class. Find the distance along that ray where it intersects that object, if it intersects at all. So if it intersects and that distance is less than the minimum value, so in this case it would be the maximum value of a double data type, set the minimum equal to the temp, so this would be the new minimum. Set hit equal to true because obviously it hit an object, as well as set the temporary color to the color of the object it hit. So once this loop finishes, we will have the smallest min value, which indicates the closest object hit, as well as the color of that object. So once that finishes, we can just add the color of that object to our base color. And then once this loops through and finishes, we can divide it by the number of samples to get the average. And then if there was a hit, we can set the buffer to that color, or we set it to the background color, which means that there was no hit. And then we made one more class, the utility or the image class, which lets us create a buffer and image on a file. So buffered image in a file, we can specify the file name, initializes everything with the following data, and then we created a method for writing the buffer data to our file, our image file more specifically, and we can specify the file type. So what I want to talk about in this episode is perspective projection. So for now what we have is orthographic projection, and what this means is that each ray that is sent out from our view plane is exactly perpendicular to the view plane. So what this creates is what's called parallel projection, and what that means is that obviously you could imagine as the rays go further and further out, so you could move your view plane, let's say 1,000 units away from the object, and it wouldn't be any smaller because all the rays go out exactly perpendicular to the view plane, so it doesn't pan out like our eyes would. There's no perspective to it. Orthographic projection is actually very useful in modeling. Like when I use Blender, I use orthographic projection a lot so that I can see if things are lined up exactly. It's also useful for, say, architectural drawings or civil engineering drawings, stuff like that. However, we're in the business of realism, and this will be eventually a game engine as well as modeling software where we can use ray tracing to create highly realistic images. So we want to utilize perspective projection. So what I'm going to do is just come in and create a new class, and I'm going to call it perspective. And this is going to extend projection. So first what we need is a constructor. Now what we need for this constructor will be determined by how we mathematically define perspective projection. So what I'm gonna do is just come in here and create some variables. I look at, let's see what else I need. Public double distance. Oops. And let's see, is that it? I mean, we could define all of the, I guess it's probably a good idea to define. Okay, so for, I want these to be vectors. And then we can import all these. Okay, so let me explain these one by one. So the eye would be I guess you can call it the camera in this. So imagine you're standing in a room, the eye would be your eyes. It would be where you're standing. That would be the point. Imagine if you only had one eye. That would be the point that we are referring to here when we say eye. Now the look at point is the point that is referenced. So let's say our eye is at 0, 0, 1, so that would be coordinate value of x0, y0, and then z1. So that means we're 1 in the positive z direction, and we want our lookout point to be 0, 0, 0. So we're staring at the origin. We could have a lookout point, let's say if you're in a room, you could be staring at the door, you could be staring at the floor, a specific spot on the floor. Now in this case, let's say you're standing still in the room, your eye value would never change, but your lookout point would change depending on where you're looking. So this would be kind of a rotation. This will come in hand later. We'll utilize rotation. Now distance is the distance between the eye and the view plane. So what you usually have is you have the eye, then the view plane, and then the lookout point. So the eye is where the camera is, and you shoot out rays from the eye, but those rays have to intersect each pixel of the view plane. So what you have is a fanning out, I guess it would be a pyramid because your view plane is a rectangle, and then you have a point, which is the eye. So it would be a pyramid on its side. You can imagine that. So you would have a bunch of rays fanning out from an eye point, intersecting each pixel on the view plane. So as you can see, when you have perspective projection, your rays fan out. So if you move an object further back, it becomes smaller because less pixels hit that object, or less rays intersect with that object. So you would have a smaller, let's say you're intersecting a sphere, you would have a smaller radius because you're further away. So you would have a smaller you would, I guess that's as simply as I could put it, you would just have a smaller amount of rays hitting your object. So you're probably wondering what these are. So when we utilize perspective projection, we need to create a new coordinate system for our camera. I guess it's called an orthonormal basis, and it's a coordinate system that you define. So I guess I'll be going over this a little bit more, but the reason we have to do this is because we need vectors created based upon these values that we defined, like the lookout and etc. And then we can convert those into our Cartesian coordinate system that we're utilizing. See if I can explain this better. So if you have a camera, you have your camera rotated in a specific, it has like, okay, let's imagine your camera is a rectangle and it has a depth to it. So it's in 3 dimensions. So it's like a square or a cube. So you would have obviously an x-axis to it, a y-axis and a z-axis, but they would be tilted in comparison to the coordinate system depending how the camera is angled in your normal Cartesian coordinate system. So in this case, if you're holding the cube, it would be rotated specifically in relation to your room. So if you're holding a cube inside of a room, we would imagine your room is your Cartesian coordinate system, where the floor is the x plane, the walls are the y and z plane. Actually, that would be z, yeah, I guess that makes sense. So you would have your cube oriented a certain amount in each axis in relation, and there's actually an equation we could utilize to convert the two. So now that we have our values, what we can do is go back to our constructor, and we can initialize, well, we can create some arguments. So I guess the first would be 3D point for the eye, 3D point for look at, and actually I think that's it. So obviously it's telling me to implement that method. I'll do that in a minute. So what we're going to do is this dot I equals new point 3D, pass in I. This dot look at equals new point 3D, look at. This dot distance, actually there's something I should have done. Okay, so we'll add that right now. So double field of view. Okay, so the distance is the distance from your eye point to the view plane, and this is actually very important because this determines your field of view. It could be field of view in the y direction or field of view in the x direction. OpenGL implements the GLU perspective in the y direction, so we'll do that too. So what you have is actually the mathematical correlation. What is it? Tangent of your angle. It's not, we'll use that for alpha. So tangent of your angle is equal to the opposite. So in this case, the opposite would be your view plane height divided by 2, and then divided by distance. So isolating that, we get this dot distance is equal to driver dot world dot view plane dot height divided by 2, and then divided by math dot tangent of math dot 2 radians our field of view. Simple enough. So now that we have those values, what else do we need to do? I guess we need to now create the orthonormal basis so that we can change our ray values into camera coordinates from camera coordinates into the normal Cartesian coordinates that we'll be using. So I guess we'll do compute UVW. So I guess so that we don't have to implement this in every, because we're going to have to do this for orthographic too, which I'll probably talk about in another episode. So we'll just create a method called, I guess it's not going to return anything, compute UVW. Oops. So what do we need to do in here? Okay, so let's see. Okay, so we need to create a vector for each u, v, and w. So what we're going to do is w is equal to new vector 3D. This just be the default value. So we can do w dot x is equal to, actually we should probably, so we want to create a vector from the eye to the lookout point. So that'll be, I guess, the pseudo z direction from the eye to the lookout point. So that's why we're using w, because that signifies z. So that would be I dot subtract lookout. And I don't know, does this return anything? Let's go back. It returns a 3D point, which I guess doesn't matter. So we can do like point 3D w point equals I dot sub lookout. So we can do w dot x equals w point dot x, w dot y equals w point. You know, I could just make a, you know what, I'm just going to do it, because although it returns a point, it doesn't really matter. I'll just make a new, so I dot sub lookout. It's going to give me an error because it doesn't return, so I'll just go in here. Actually, I'm going to have to call this something else because of Java's, so this will be vector 3D sub vec, so this will be point 3D point, and then just copy this. So it's basically the same exact representation mathematically. Vector 3D. Mathematically, a vector and a point, in the way we described them in Java here, x, y, and z, are exactly the same. So that's why I'm allowed to do this, even though technically this would, I guess that does make sense actually. You can create a vector from subtracting 2 points. just going to save that, and this should no longer cannot convert from 0.3. Oh, that's fine. So subtract vector. So that gives us W. That gives us the vector from the eye to the lookout point. Now from there, we want to normalize this, because when we're talking about coordinate systems, all of our coordinate axes are normalized values. They're all unit vectors, I guess what I mean to say. Then we have u is equal to, what's u equal to? We need like an up vector, and then we need to cross that with w, what we already have. And then we can normalize this. So we need an up vector. Okay, so the reason we need an up vector is we already have the z reference. So we need to cross w with u, and u would be the way we're going to make u is by how am I going to explain this? Let's see. So we already have w, and we need to cross that with some form of an up vector, which would give another vector which is perpendicular to both of those, so that we can create u, and u would be our y direction. So our up vector would be something like something like that would work. You don't want an up vector that is exactly 0, 1, 0, because there may be obvious times when you need your camera pointing directly up, and that would actually cause the up vector and u to be parallel, which would obviously cause a problem when you try to cross it. So we have w now, which is the vector from the eye to the lookout. We have u, which is perpendicular to w, as well as the up vector. So this u would be a general up direction. And then finally we need v, which would be the cross between u, right-handed system. So this would be w cross u. If I did u cross w, it would give a left-handed coordinate system, and we want a right-handed one. So, and then you don't need to normalize v because u is already normalized and w is already normalized. So the cross between the two would give you normalized value. But better safe than sorry. So here is the method to compute our orthonormal basis. This is w, which is the vector from the eye to the lookout point. We normalize this, and this gives us our pseudo z vector. Then we define an up vector, which is almost exactly up in terms of 0, 1, 0. It's off by a little bit, as I said before, because sometimes we want our camera pointing position perfectly up, which would cause problems. So what we do is we cross the up vector with the z vector we created, and this would give us a vector that's both perpendicular to up and w. visualize it, obviously, and then from there we cross W with U, and we get V, which would be the pseudo x-axis. So that's it for our compute. I feel like I didn't explain that enough. I mean, these concepts make sense to me, but when you're trying to explain it to a general programming, well, I guess it's not that general. If you guys are watching this and following along, you probably know these concepts and this kind of mathematics. I mean, I would hope so. This is basically 3D programming. It's going to get more complex when we talk about materials and lighting. I guess in the next episode at the start, I'll explain this quickly again in a better fashion, but so far it looks good. So what do we need to do next? So I guess we can go back, and now that we've computed our camera coordinate system, we can, what's going on here? Oh, it's just giving me that error. So create ray. This takes in a 2D point. There we go. Okay, so now what we can do is create our rays. So I guess what we could do is just create a new ray, and our point, the starting point for our array would be the eye. So new point 3D, we'll just pass an eye. So like I said, the eye is our camera position, and every ray in our loop is going to originate from this point. So this would be the origin. And next is we need to define the vector. Now this determines the direction as well as the magnitude of where our ray is going, which is going to make sure that it intersects the view plane at the proper pixel. So we can do this actually by utilizing that orthonormal basis that we just defined. So we can do u dot, actually I don't think I created, that's no fun. So I'll have to go in and create a multiply method. So multiply, pass in a double value. Let's call it a scalar, I guess. So x times equals scalar, y times equals scalar. So this is going to multiply each component in our vector by a certain scalar value. Actually, you know what? Because this would be... So we want to return a 3D vector. That's not going to work because we need to pass in a vector for when we create our array. So we'll just do return new vector 3D x times scalar, y times scalar, z times scalar. So we can do it that way, which actually makes more sense. So let me just type this out and then I'll explain it. I think it's, what is that, V or W? Actually, this would be add. What am I talking about? This would be add. And this would be point.y. This would be subtract. W, and this would be multiplied by the, actually this is negative distance, because we want the reverse of I minus look at. So I think I need more parentheses, one more. There we go. I type vector, it's direction. Okay, let me just. Okay, so we created our point for each ray, which is the I. Now this is probably very confusing. So what we do is we take the U portion of our orthonormal basis, and I guess I explained this slightly incorrectly earlier. So I ordered them incorrectly in here. I should have ordered them accordingly so that they follow the X, Y, and Z. So we have the vector, the unit vector of our orthonormal basis that we created, which corresponds to the camera. So we're going to multiply this by the X, the coordinate value X that we're passing in. This is the X point we determined in our sampling for anti-aliasing. What this is going to do is translate this X point from our orthonormal basis coordinate system into the normal Cartesian coordinate system that we're using. And then we're going to add that value. So this would be, this initial vector is, this is all X, and then Y is 0 and Z is 0. So we're going to add to that V multiplied with the Y portion. So this would be now X and then Y and then Z is 0. So this means that we're taking the pseudo y vector from our orthonormal basis, which corresponds to the camera, and multiplying that value so that we can convert it by the y value of the point we're passing it. And then finally we're subtracting this so we can get okay, that's why I subtracted. So we're subtracting this so that we can get the negative direction, because we want a right-handed coordinate system. Right-handed coordinate system would actually correspond to look at minus I instead of I minus look at, but I think it makes more sense this way, and then just to create the negative of that. So we would subtract the W, which would be the Z portion, which is multiplied by the distance, which gives us the converted values. So what this U multiplied by X and V multiplied by Y and then W multiplied by distance, this is converting between our two coordinate systems. And in this way we can create our vector, which determines where we are intersecting the view plane, which is all determined by the point we're passing it, because that is the specific point on the view plane that we are sampling right now. Then obviously we need to normalize. It's always important to normalize in graphics, and then we can return the ray. So I think that's correct. Let me just change this because I had a preset value earlier. That's actually one that I found in Raytracing from the ground up. It's actually a really good book. You guys should read it if you haven't, but it gives a good value for this up vector. So this is 00424, and then this one is 764. I guess it would make sense to make this a global variable and then access it instead of creating it every time, since memory access is probably quicker. Okay, so I guess we can try this now. We can go back here and do perspective. It's probably going to ask us to import. So we need to create an eye point, so let's just make this something like that. The eye point will be 600 away along the z-axis. Our lookout point would be the origin, which is what our spheres are centered around. And then a field of view, I think 90 would work. We could try that and see how it works. Feeling it's not gonna work. And no, it did not. Let's take out the plane and see what happened here. Oops, what did I do? 1.0. Well, we'll just try scaling it back because that might be causing a problem. I don't think so though. Let's get rid of the world. Or let's get rid of the plane. So I mean our spheres should be showing up. Oh, that's probably because I'm in a different, let's see. When I did this earlier, I had this perspective. When I defined the distance, I utilized the X field of view instead of the Y. So that might be causing a problem. Let's change this field of view. Let's see. I mean, a larger field of view should there we go. My field of view was too large, so it was too far away. Like I mentioned, the field of view determines the distance from the eye to the view plane. So if your field of view is too large, the objects are basically going to be, there's going to be less rays to hit the objects, so you probably won't see your object. So what you'll probably do is make this smaller. This will probably give me a closer picture. Yeah, okay. So that's the tricky part, converting from X field of view to Y field of view, because it actually makes a difference in how you see the objects. When we have, if we utilize the X field of view, I actually have to make this larger. So this is going to be something to keep note of as we get into the rasterization with lightweight Java game library, and when we start making our modeling software in combination with the Raytracer. So let's just get rid of the orthographic. I'll probably talk about implementing that one next time, since I'm already probably at what, 30 minutes? 38 minutes, yeah. So what we can do is let's add that plane back now that I figured out what was wrong. Let's go to the driver. What we can do is let's do like -200 and then maybe up a little. So this would be moving your camera to the left and up a little bit from the previous image we had. There we go, and that worked. So there you have it. This would be like straight out like we were before. Actually, it would be more like this would be straight out like we had before. So we're rotating this way and then up. So if you can visualize it, this makes perfect sense. So that means we're correct. Actually, I think they're, you know what, I'll just talk about it in the next episode. In the next episode, I'll explain this one more time. I'll run through it, and then I'll implement the orthographic one utilizing this orthonormal basis. Because as we have it now, this is just projected along the z-axis, and we want to be able to project it anywhere. So yeah, thanks for watching.